harmonic motion, okay? And we're going to end up comparing that K value to a K value that we get with simple harmonic motion. So have you heard of this simple harmonic motion before? Okay, physicists call this SHM. All right, so this is SHM. And here's what it's going to be. I don't know how much we tell you to put on there. 250 for one thing. So I have there 250. So you're actually going to do more than one investigation here. So now I'm paying attention to the mass of the weight hanger. So I just put 250 grams in addition to the 50 grams of the mass hanger. So now this is 300 grams on here, okay? Everybody's with me on that? There always seems to be some confusion because you ignore it in the first part, but you pay attention to it in the second. Now here's what you're going to do. Here's simple harmonic motion. Up and down, okay? And it's a very well understood motion by physicists. It turns out that if you graph the motion, you're going to get, wait, let me give myself a couple cheat so I can draw this well. It's going to be, you know, like a nice sine curve, or it can be a cosine curve. It can, you know, it can be shifted one way or the other. If motion obeys that sine curve, it's simple harmonic motion. And you can see it's still going, right? Now, what we really have going on here probably is a little bit of damped simple harmonic motion. And damped means that the amplitude is getting smaller. So what we probably, if we look at it on a smaller time scale, we're probably getting something. Let's see if I can do this. Make my little envelope here. Like watching paint dry. Okay. So what happens over time is the amplitude gets smaller and smaller, and that's because of, what's that F word? Friction. Force is one too. But you can make this happen even faster if you put, like, if we had a piece of cardboard and we put a big piece of cardboard on there, that would really increase the air resistance and it would damp. That's called damping, okay? This is called damped harmonic motion. But there's not going to be a lot of damping while we look at it. So what we're going to do is time to get the period. Remember what the period is? It's the time for one complete oscillation. And we're going to get that for several different situations. And then you're going to make two graphs. Well, wait, let me tell you the whole thing. Okay, first of all, you might think that the period would depend on the amplitude. Okay? It seems reasonable, maybe, if you don't understand it, if you haven't played with it before, to think that it might matter if I do a small oscillation, that might have a different period than if I do a big oscillation. You might think a big oscillation would have a bigger period. Well, it turns out, and I guess I should be letting you discover this, but it turns out that it doesn't matter how big the oscillation is. It's going to have the same period. Even though we're going to have you do this just to verify it, okay? So the first experiment here on page 62 says period dependence on amplitude. So, I mean, we're interested in the period. What affects the period? And remember, the period is the time for one complete oscillation. So that would be like a down, up, down. Starting from down, up, down. That's one period. So you're going to check amplitude. That's the first thing you're checking. So that's how far you stretch it before you let it go. And then the other thing you're going to check is mass. The mass that you hang on the end. Okay? Does mass affect it? And it turns out mass does affect it. And in fact, mass is the main thing that affects it. Let me show you what happens when I add 200 more grams here. Now, I hope you had a sense of how fast it was oscillating with 300. Can you tell if that's slower or faster?
Slower.
It's slower. And if you think about it, it's got more inertia, right? Because there's more mass there. In fact, they used to use something called an inertial balance to track the masses of the astronauts when they were on space missions. Because if you're in an apparently weightless situation, you can't just go step on a scale. They had like, I think it was called an inertia scale or something. They would have them sit in a scale or sit in a chair, and then they would give the chair, it was hooked on springs, and they would give it like a sideways motion, and they would oscillate back and forth, and they would actually measure the period of the oscillation, and then they could tell what the mass of the astronaut was. So just a little fun fact.
What's
yes.
one oscillation again? How many times does it happen?
One oscillation is like from one position all the way through equilibrium back to the same position. So when it's not oscillating, I guess I should make sure you understand this. When it's just hanging there, that's the equilibrium position. And then if you displace it from here, you can 0, 1, 2, okay? So like if you're doing the stopwatch, when you start the stopwatch, that should be the position you're always going to let it go back to when you count. And you call that first one 0, and then 1 when it's made one round trip, and so on, okay? All right, now let me tell you, just like all the other labs you do in here, physicists have already figured out how these things impact the period. And in fact, it's a pretty well-known relationship. The period is equal to 2 pi times the square root of the mass that you have hanging on there divided by the spring constant. And I mean, you can derive this formula, but we're not going to derive it today. We're just going to test it. All right, this is the actual relationship.